So you take them like, blah, 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 not English. Hello again. Did you miss me? I know some of you did, because I've been getting a lot of messages about continuing this series, but that's okay. I realize people are excited about it. I think I dropped the first part of this series a little bit prematurely. Not that I knew it would be, it's just a whole lot of things came up between that video and this video. So anyway, welcome to part 2 of the 32-bit series. And I knew this video was coming. I didn't know where in the series it would be, or if I was going to make it like a 5-minute data dump or a Talk Nerdy to Me video or something like that. But I knew I had to do the basics of what that means. What does 8-bit mean? What does 32-bit mean? So that's going to be this one. So if you're already a coder, or if you're familiar with programming microprocessors, or if you're just old enough that you remember 8-bit computers and the evolution through 16-bit, 32, 64 and all that, then you could probably tune this out or just kind of skim it or let it run in the background. But for the rest of you, I'm just going to go through and hit the very basics of what these mean. And by doing that, you lay the foundation and then realize what you can accomplish with different types of processor architectures. Because when somebody says something like, why would I need a 32-bit printer? Do I need that? The answer is always like, I don't know if you need it. You need it if you need it. Now, I'm not in any way pitting these against each other and saying one good, one bad, because both are fine, again, depending on what you want to do with them. So anyway, enough of the intro, let's get into it. Now, we've all heard the term bit before. It's just a size. It's a subdivision of data. So there's like nibbles, bits, bytes, and then you have kilobytes, megabytes, gigabytes, etc., etc. So when we're talking about bits, we're talking about very, very small pieces of information. And really all we're saying when we say 8-bit or 16-bit or 64-bit or 128-bit or whatever, that just designates the number of bits of data that a particular processor can crunch at one time. And that relates to word size. And when we're talking about words, we're not talking about words like and, if, for, nor, yet, but we're talking about data words. And whatever data word matches your bits, that's your natural word size, i.e. the type of word that's used in the basic processing on that particular processor. So if we're just talking about the word size, we're pushing with 8-bit, 8 bits at a time. So we're pushing this much data. With 32-bit, we're pushing 32 bits at a time, so that much data. And then when we're talking about memory addressing, let's stop right there. I did explain on a whole section how memory allocation works in a computer. Instead, I'm just going to explain how it works in an Arduino, because it was like 20 minutes long and boring. Alright, so in our MCUs, here's what we the way that the memory works. We have our flash, which is the big chunk of memory, the prog mem, that's your static storage, and then the SRAM, which is your read and write storage. And that is divided into your heap, your stack, and then your static memory. A static holds your globals and your static variables. The stack holds your local variables and your function calls, and then the heap is just dynamic allocation. Now let's get a visual representation of what that's going to look like. So we have our stack on the top and our static on the bottom, then we have our heap and our free memory. And our stack and our heap are going to swap in and out of that. Your flash is where your program memory sits, that's where all the code that you stick in there goes, and on our Uno there's only 32K. On a Mega there's 256K. Now, in contrast to that flash, our SRAM, our Uno only has 2K, and our Mega only has 8K. And that is also an issue when you're talking about these, because even though you might be able to fit something in flash, you may not be able to fit it into your SRAM memory, and then you're going to get what's called a stack crash when you run out of that. And that equals either Wonksville or random resets or other bizarre behavior. Even though we may be able to fit the program into the memory, we may not be able to fit the function into our RAM when we need it. So moving further into the natural data unit, the Arduino MCUs that we're used to, the Atmels, they use integers as their native data unit. And if you don't remember from arithmetic what an integer is, it's a whole number. Now, we have integers and unsigned integers. Signed just means negative or positive, so negative whole numbers, positive whole numbers, that type of thing. And that particular family of chips that we're used to doesn't have any built-in support for floating point operations. Now, old-timers out there will remember when we used to have 8-bit computers that had separate floating point unit processors or coprocessors on the motherboard to do those types of operations. Now they're built onto the die. But regardless, as a result of that, the compiler has to jump through hoops if it's going to do the types of math that we need it to do, especially when it gets very complex and you have movements that are required in like a Core XY machine or even worse, a Delta machine. And those machines tend to be able to move faster. Those kinematic platforms move pretty fast, the Deltas, because they have a really lightweight printhead. So you're asking this processor to do non-native math using more complex equations than we have to in a regular Cartesian machine, and you're asking it to do it a lot quicker. So that's why many people have noticed that they just run out of horsepower on a lot of these traditional 8-bit chips. Now, of course, there are ways around the speed limits, and I will get to those in future episodes. One option is using, like I mentioned before, a former like Clipper who does the math on a 32-bit computer, and then it sends that out to your 8-bit MCU. Another option is to set your stepper drivers down to a larger step size, like instead of 16 times microstepping, you can use quarter stepping. And then if you're using a chip like a Trinamic chip who has a lookup table that lets you do 256 times interpolation, you can smooth that quarter stepping back out so it's nice and quiet, those types of things. But again, we'll get to that in other videos. Now, 32-bit MCUs don't necessarily have floating point. Another bus. Now, 32-bit chips won't necessarily have floating point operations built in, but some do. Like I think the Cortex M4s do have, they support floating point operations. But even if you don't have an FPU, if you have enough memory space and enough horsepower, you can still muscle your way through it a lot better and have plenty of headroom. There's also a thing called data instruction sets, or just instruction sets. And what that refers to is what the chip is able to do by itself just through the machine calls, the assembler calls. Because all these units, they just do math by moving data from one memory register to another and shuffling things around, comparing to each other. It's just a whole bunch of logic gates holding hands on a silicone wafer. So it's very possible that certain operations aren't natively supported. So a lot of work goes into writing code for 8-bit processors that cuts a lot of that stuff out. Like square roots are goofy, even division is goofy. Addition, subtraction, it's usually okay with that. Addition's the quickest, multiplication's pretty fast, but you're really dependent on the compiler software to do a lot of the shuffling and twiddling to make that math happen more quickly, and squish that into a format that's easiest for that processor to digest quickly to take the fewest CPU cycles possible. Or just to make it possible at all. So what if we had one big 32-bit chunk of data? Well, we'd have to break that down into 4 8-bit pieces of data and feed those all in one at a time, which takes longer. And if you end up having to jump through hoops because you don't have a specific function that you need, instead of just being able to do something easy like 2 raised to 8 equals 256, you end up having to do something like 2 times 2 times 2 times 2 times 2 times 2 equals 256, which takes up a lot more space. And as we've already seen, RAM and memory are already at a premium. And I know that was a bad example because all I did was unroll the math, but just roll with me here. Now, if you spend any time on the Arduino forums, you'll find all kinds of sketches that you can upload and benchmark how quickly your particular processor can handle certain operations. So one example is if you take a test of multiplication and use different word types like byte, long, float, run that on your 8-bit Arduino processor. Special note here, I actually did write that code and I actually did do the tests on my lunch break with an actual Uno. But I made an executive decision to cut it because it was long and boring. So you can thank me for that later. Now back to your regularly scheduled video. If you use a byte, that takes 4 microseconds. If you use an integer, it takes twice as long, 8 microseconds. And then if you use a float, it takes 12 microseconds. So you see that just using the different word type because of the size of those and the way that it has to abstract the mathematics and shuffle things around in the memory increases the time that it takes to compute that operation 4 times. And that's just multiplication. Let's look at something that we don't have built in like division. Now, division is slow to begin with, so just to do a byte takes about 16 microseconds. So when you move to integers, it's 20 microseconds, which isn't all that much longer than a byte, but if we try to use floats, it goes all the way up to 48. So comparing like doing byte multiplication versus float division is 12 times slower on an 8-bit processor that doesn't have an instruction built in for division. And notice here, we haven't mentioned anything about clock speed. So all this is saying is like per cycle relative to the word type you're using and the operation you're performing on those numbers, you're going to get higher performance with A versus B. See what I mean? So now we have to get into clock speed. As we know, our trusty megas are clocked in at 16 megahertz. Now, if we just move on to like a Cortex M4, the STM models go up to 168 megahertz. The M3s up to 120, and even the humble M0s will go up to 48 megahertz, which is still a lot faster. Then we have these fire-breathing monsters like ESP32 chips that are clocked all the way up to 240 megahertz, and they're dual-core. Which brings us to another thing, SMP, so symmetrical multiprocessing. That's possible with 32-bit architectures, whereas it's just not with 8. And that's not something that's been taken advantage of, but it is there for future use. If you're familiar with the inner workings of Marlin Firmware, you know that the fastest we can work with is 40 kilohertz. Now, if you've ever wondered, why is it we can only work with 40 cycles a second, in terms of like stepper pulses, I mean, the board works off of a 16 megahertz crystal. Why isn't it so much faster? Well, the pulses going out and the interrupts coming in, the actual hardware interrupts, have to be extremely precise. We can't just kind of math it out. It's tied into the actual hardware timers, and that is tied to the system speed, but it isn't equal to the system speed, obviously. And I know I greatly simplified the timer interrupt issue. Sorry. The nerds out there are going to come at me with pitchforks and torches. But also in terms of speed, you have a couple different clocks, but just talking about your system clock, your sys clock, that's going to determine speeds for your peripherals, like take SPI for example. Like SPI running in master mode, you can run at your sys clock. So since we're talking about like buses and interfacing, let's talk about different features that are available on those boards. Generally, if you need something small that doesn't crunch a lot of math and has just a few things connected to it, an 8-bit processor is fine, because typically they're lower cost, lower power, and have smaller memory requirements. That's not always the case, but typically, and that's what makes them great for little experimenter boards. And as we know, an average Cartesian 3D printer running at like moderate speeds, like, i3 type speeds, we can get along just fine. But what happens when we start wanting more speed? Or what happens when we start wanting more features? What if we want several SD cards? What if we want several displays? What if we want a couple different types of communication running simultaneously? We've already run into problems with certain boards where it's tough to get your Trinamic TMC 2130s that run off your SPI bus to play nicely with your LCD screen, because they have to be transmitted data at different rates. You have to feed the screen very slowly, whereas your steppers have to run in whatever speed you're running your steppers at. And we kind of get around that by splitting them like one to the other on a hardware SPI, and then like BitBang emulate a software SPI bus and send it out to another one, and write a kludge in a library around the issue and that type of thing. And it gets even more complicated when you have an SD card and Wi-Fi and Bluetooth and all that stuff. So with 8-bit chips, we could add a whole bunch of coprocessors and application-specific processors on there, add extra buses and that type of thing, but that's not where the demand is in the market, so those chips really don't exist. Whereas the 32-bit stuff right out of the box has a plethora of different bus options. Now, does that mean that 8-bit is bad or can't handle it? No, not necessarily. Like I said at the beginning, if somebody asks, like, why do I need 32-bit? Well, you need it if you need it. What do you want out of it? Are you running do you want to run a color touch screen with 2 different SD cards and Trinamic drivers and all the fancy trimmings? Or do you not care? It's completely up to you. So along those hardware lines, let's also talk about memory. Now, if you look back at some of my videos, you see one where I was trying to explain how you can shave features off of Marlin to try to fit some modern features onto one of the smaller boards, like the Melzy boards that come on a lot of like, you know, like the Enders and things like that, because they have very limited space in terms of, you know, program memory, 128K. The Megas have twice that, but a lot of the 32-bit chips coming out these days have many, many times more of that. So to give you an idea, you can go just peruse that video, skim through it, and say like, okay, well, there's 6 different types of bed leveling. Like, do I want the one that draws a really fancy mesh and then does a whole bunch of interpolation to extrapolate data points and saves that in memory, and how much debugging do I need? And also other things like the BL touch sensors, they use up a huge chunk of memory. Graphical LCDs, those libraries involved use a huge chunk of memory. Do I want a custom splash screen? Do you need all that? Well, not necessarily, but you might want it. Now, to show you the difference in memory size, let's look at the flash and the SRAM. So our Mega, we know, has 256K of flash and 8K of SRAM. Now our M4 has 1 meg of flash and up to 192K of SRAM depending on the chip. The M3s have also up to a meg of flash depending on the chip and up to 128K of SRAM, which is already getting into bonkers territory compared to our 8K. Then we look at the ESP32s that have up to 4 megs of flash and then up to 512K of SRAM, which is bonkers. And that's just all on one of these tiny little critters that cost the priestly sum of $6.80. So we've gotten to the point where if you want fast and a lot of things and fancy, it just plain doesn't fit on the old boards anymore. Whereas the 32-bit chips, although they are coming with small amounts of memory for the really cheap ones, like you can get them with 64K and 128K. They also do come with like a couple megs of program space. And while we're talking about peripherals and onboard things, most of the 8-bit processors that we use, like the Atmel chips, don't have built-in USB. If you look on the board, a lot of the times they have a coprocessor or a helper chip. Like on the genuine Arduinos and like the better clones, you'll have like the 16U, which is actually another 8-bit chip that they're just running as a USB bridge. So it's taking the data from the virtual COM port on your computer, sending that to the 16U chip, which converts that to serial and then sends that to your Atmel chip. Or with the clones, it'll be like a what are they, a CH340G, like that's usually what they use, which are slower and they misbehave and you have to use custom drivers for them, but whatever. Whereas most of the new 32-bit chips coming out, they have native full-speed USB built in, or even native high-speed USB built in, depending on the chips. A lot of them have DFU bootloaders burnt right onto the silicone, so you don't have to worry about bricking them if you do something stupid. You just boot it up into whatever its recovery mode is, then you're back into DFU bootloader and you can reflash your firmware and then reflash your program or your user files and all that stuff. Now, some of the stated benefits of the 8 bits over 16 bits are that they're cheaper and more energy efficient. Now, the second one's debatable, and the first one is not true in our case, which is unfortunate. Basically, Atmel has a monopoly almost on the 8-bit processors that we use for these because it's all based off of Arduino. And since they control the whole deal from soup to nuts, they can set those prices wherever they want. So just getting, if you want to buy a genuine Atmel chip, like without the board, it could cost you like, you know, $8 to $12, even up to 16 for some of them, just for the chip. But there's no reason for them to cost that much. Whereas some of the 32-bit chips, like if you look at the STM32 boards for the M0s and the F1s and things like that, those are in quantity like pennies a piece or $1 a piece, something like that. So that kind of blows that benefit out of the water. So why is it that we haven't seen everyone move completely from 8 to 32-bit yet? Well, first off, for a lot of use cases, like I said, 8-bit works just fine, and if it ain't broke, don't fix it, or so the manufacturers would say. And other than that, it really just comes down to support and availability. Now, when I talk about support, I don't mean like customer support, like warranties or things like that. I mean the libraries that you have to install with your firmware to run a particular peripheral. they're already developed for 8-bit, whereas they either may not have been ported yet to 32-bit, or they may never be ported, or may not be possible to be ported. Also, the IDEs you were used to working in, like the Arduino IDE, that's all optimized for like I said, the integer twiddling and optimizing for 8-bit bandwidth. So we have to move into more unfamiliar territory, like a lot of people have moved on to, like, you know, Platform IO and VS Code and those types of things. And most importantly, the firmware is very mature on the 8-bit stuff, and it's still fairly new-ish on 32-bit. Now, you have some firmwares like Teacup that really don't care what they run on, as long as you get the ports right. We have specific firmwares that are built around specific boards with specific processors on them. An example would be SmoothieWare and RepRap firmware. The boards that they support them very well, which are the boards that the developers of that firmware, the ones that they sell. And there is limited support for other boards that have been added in by the community, but really the thrust is making them run well on their boards. There's also one of the first 32-bit printers, which I actually have one around here somewhere, is the Malion M200, or it's also called the Monoprice MP Mini. That had an STM 32-bit chip on it, and you can install Marlin 2 on that, but they used a proprietary firmware, and they have been for years. They've had a 32-bit operating system on there for years. They just base it off of Gerbil and then built their own firmware on top of that, and have a separate chip for the UI that has its own firmware and that type of thing. And that goes for a couple other boards that are similar that are coming up from Asia as well, where they have their proprietary firmwares that they run off of. But they are 32-bit, you just can't change them unless you manage to shoehorn Marlin on there somehow. But that part of the industry migrating to 32-bit boards is going to happen, and is happening as the libraries and the firmware are developing and becoming more solid, more dependable, more available, easier to use, that type of thing. So there you go. I know that probably doesn't answer all the questions, and for some of you watching, it might not even, maybe you're more confused than you were when I started. But that's just the nuts and bolts behind it, with a little bit of conjecture at the end. So again, 8-bit, 32-bit, different architectures, different sets of features that are typically available on them, the amount of memory they can address, the speed that you can run your buses at, the speed that you can run your interrupts at, native networking, and available code. It's basically what you have to know. Hope that clears up some mystery for you. If you have any questions, leave them in the comments below. I'll try to get to them when I have time. I don't have a lot of time these days, but I do try. I might be a week late answering, but you know, I'll do my best. And I'm sure there's a lot of nerdlingers that can jump in there and answer questions for you as well. I promise the next video won't be theory. We'll get into some actual stuff that's out there. As always, this channel is supported by you. These videos take a long time to make. And if you want to see me keep making these, or you want them more frequently, make sure that you check out my support links in the description below and under all my videos. There's Patreon, PayPal, Amazon Portal, all their usual stuff. You know the deal. So thanks for watching, and until the next video, get out there and make something awesome.